In this video, we're going to be looking at empirical formulae and how to calculate them based on data. So the first thing we have to understand is what is the empirical formula of an element. So if we take a look at this first example, we have C6H12O6. Now the empirical formula is basically where we express all the elements in their simplest ratio. So for example, in this case, the ratio of the elements from C to H to O is 6 to 12 to 6. And of course, this can be simplified. If you think about it like a fraction, if you have 6 over 12, that can be written as 1 over 2. So in this way, 6 to 12 to 6 can be written as 1 to 2 to 1. So for every 2 hydrogens, there's 1 carbon and 1 oxygen. So the empirical formula, hence, would be CH2O. So for the compound here, which is glucose, the empirical formula is CH2O. And we can do the same thing for the other ones. So for C2H4, just write down the ratio, which is 2 to 4, which is equal to 1 to 2. So the empirical formula of what is ethene in this case is CH2. So in this case, we have to just try and get each of the compounds down to their simplest form. Now we have H2 over here. So the ratio is 2 to 1, which cannot be simplified any further. So the empirical formula of H2O is still H2O. So with this next one, we have C3H8. So the ratio is 3 to 8. And that can't be simplified any further. So the empirical formula is still C3H8. And finally, with C6H6, which is benzene, well, the ratio is 6 to 6. And of course, we know that's 1 to 1. So hence, the empirical formula of benzene is CH. Okay, so this question asks us to determine the empirical formula of a compound with 40% carbon, 6.7% hydrogen, and 53.3% oxygen as percentages by mass. So in this example, we're going to use data to determine the empirical formula of a compound. And this may be asked in a chemistry exam. So basically, what we have to first realize is that we've got a couple of unfamiliar terms. So this one, percentages by mass. What that means is that if you have a set amount of a substance, then that substance makes up that percentage by the mass. So for example, if you had 100 grams of this compound, well then, as we see over here, 40% of that would be carbon, which means that 40% of 100 is 40 grams. So 40 grams would be carbon if there was 100 grams of this compound. And we also have to realize that each of these elements have molar masses. So these molar masses are ultimately what's contributing to the mass. And we have to figure out how to integrate those molar masses to get ratios that we can then use to get the empirical formula. Too much? No worries, we'll slow down a bit. So we're told that we've got 100 grams of a compound. That's what I would always use because it's easier to convert percentages to gram values if you're using 100 grams. So 100 grams of a compound. Of those 100 grams, 40 grams is carbon, 6.7 grams is hydrogen, and 53.3 grams is oxygen. And now, what we have to also realize is that 40 plus 6.7 plus 53.3 is equal to 100 grams, which means that there is no other element present in this compound. That means we can express this compound as CXHYOZ. This is empirical formula representation. X, Y, and Z are constants that we have to figure out. And this compound, ultimately only contains carbon, hydrogen, and oxygen. Great. Now what we have to do is write down the molar masses of each of these elements. So carbon is equal to 12.01, hydrogen is equal to 1.01, and oxygen is equal to 16. Now, using these molar masses, we can express carbon, hydrogen, and oxygen in a ratio. So ultimately, we want the ratio to be X to Y to Z. So to do that, we have to do the mass divided by the molar mass. And this will give us a ratio. Because we want to figure out how many atoms of this carbon make up the 40 grams. So 12.01 times what will give us 40 grams. So let's do that right now. So moles of carbon, we're going to express this as moles because mass over molar mass is moles. So moles of carbon is equal to 40 over 12.01. So the moles of hydrogen is equal to 6.7 over 1.01, and the moles of oxygen are equal to 53.3 over 16. And now we're going to just do these calculations. So for carbon, it's 40 divided by 12.01. Just plug that into a calculator, and you get 3.33 approximately. It goes on. Now for hydrogen, if we do 6.7 divided by 1.01, we get 6.63, and then there it goes on. And for oxygen, 53.3 divided by 16 is 3.33. And it goes on. So now, it might be obvious by now, but the ratios seem to be a little bit too nice, honestly, because if we put them into the ratio 3.33 to 6.63 to 3.33, now what we have to do is express these in terms of whole numbers, because decimals, we can never have decimals in a compound. We have to represent all the subscripts as integers. And the way to do this is to divide it by the smallest value, because that will make that value 1. So 3.33 divided by 3.33 is 1. 6.63 divided by 3.33 is 1.99, which is close enough to 2, so I'm going to round it to that. And then 3.33 divided by 3.33 is also 1. So we've got the ratio as 1 to 2 to 1. So x is 1, y is 2, and z is 1. Hence, the empirical formula is C1H2O1, but we're going to represent that as CH2O. So in this case, the empirical formula is basically that of glucose, but we can't be sure what compound it is specifically, because the empirical formula can denote a wide range of compounds. CH2O could denote the empirical formula of C4H8O4 or C6H12O6. Whatever has the ratio 1 to 1, 1 to 2 to 1 will have the empirical formula CH2O. So this is our answer. Okay, so this is the last question we're going to attempt, and it should hopefully give you an example of a much harder empirical formula problem you could come across. So menthol is composed of carbon, hydrogen, and oxygen. So a 0.1005 gram sample of menthol is combusted, producing 0.2829 grams of carbon dioxide and 0.1159 grams of water. Given menthol has a molar mass of 156.27 grams, determine its molecular formula. So, of course, given that it has carbon, hydrogen, and oxygen with subscripts we do not know, menthol can be written as CXHYOZ, where we don't know the values of X, Y, and Z, and we're trying to find those. The formula of the combustion reaction can be written as CXHYOZ, obviously we're representing menthol, plus oxygen, combust to form carbon dioxide and water. So I haven't included any of the coefficients because we can't figure them out yet. What we have to do is just work without them. So if we look at our products, we have carbon dioxide and water. So carbon does not exist in water, but it does in carbon dioxide, which means that all the moles of the carbon used in this reaction will only be in the carbon dioxide. So if we find the moles of carbon dioxide, we can figure out the moles of carbon. If we find the moles of carbon dioxide, then the moles of carbon dioxide will be the same as carbon because there is one carbon atom in every carbon dioxide molecule. So let's just do that. Moles of carbon dioxide, which is equal to moles of carbon, is equal to the mass of carbon dioxide, which is 0.2829, divided by the molar mass of carbon dioxide, which is 44.01, which gives us 0.0064 moles. So now let's do it for the hydrogen. So the hydrogens only exist in the water. They are not in the carbon dioxide, and hence, if we find the moles of water, we can figure out the moles of hydrogen. So there are 2 atoms of hydrogen in every water molecule, which means that the number of moles of hydrogen will be double the moles of water, as for every water molecule there are 2 hydrogen atoms. So moles of H2O equals half the moles of hydrogen, which is equal to, so the moles of water is 0.1159 divided by the molar mass of water, which is 18.02, which is equal to, just putting in the calculator, equal to 0.0064. So the moles of hydrogen, therefore, are 2 times that amount, which is 0.0129. So actually this part here was going for more decimal places, and when we multiplied it, this became a 9 instead of an 8. All right, no, that doesn't matter too much though. Now we can move on to the oxygen. So what we need to do is first figure out the mass of the carbon and hydrogen present in the products, because unfortunately oxygen is present in both these molecules. So if we figure out the mass of the carbon and the hydrogen, we can figure out the moles of the oxygen, since we know how much menthol was used. So the grams of carbon are basically equal to its moles times its molar mass. So that's 0.0064 times 12.01, which is equal to, just putting in the calculator, 0.0769 grams. Let's do that for hydrogen as well. Grams of hydrogen are equal to 0.0129, which is the moles, times its molar mass, which is 1.01, which is equal to, I'm just putting in the calculator as well, 0.130 grams. And now we know that the mass of the oxygen is 0.1005, which is the mass of menthol, minus 0.0769 grams, minus 0.130 grams, which is equal to, I'm just going to put this into the calculator, which is equal to 0.0106. Oh, sorry, also I accidentally wrote this wrong. It's meant to be 0.0130. Same thing for this part over here. Sorry for my math. Anyway, so now we have 0.0106 grams of oxygen. Now we can figure out the moles of oxygen. So we just multiply it by the molar mass. So 0.0106 times 16. Sorry, we divide it by the molar mass. So 0.0106 over 16 is equal to 0.00066 moles. And now we can express our menthol subscripts in their ratios. So we're going to do C to H2O is equal to 0.0064 to 0.0129 to 0.00066. So if we divide by the lowest value, which happens to be 0.00066, we get 0.0064 divided by 0.00066, which is 10. Then 0.0129 divided by 0.00066 is 20 to 1. So because 0.00066 divided by itself is just 1. So that means the empirical formula of menthol, empirical formula is C10H20O. But we're not done there. We have been told that the molar mass is 156.27 grams. So we need to find the molar mass of this over here. So the MR of C10H20O is, so we just do 12.01 times 10, since that's the molar mass of carbon, times 10, plus 1.01 times 20, we're adding the hydrogens in, and then plus 16 from the oxygen, which gives us 156.3, which is the same as this. So although we've gotten an empirical formula that has a molar mass of 156.3, and it's the same as it's the same as the molecular formula's molar mass. It just means that menthol is in its simplest form already. So therefore, menthol is C10H20O. So the empirical formula can be the same as the molecular formula, because in this case, obviously 10, 20, and 1 cannot be simplified further, and it is possible for a compound to have the same empirical formula as its molecular formula, but it's not always true. That's what we're trying to prove here.